3 sections we're doing today?
We are doing 3 sections today, 9.2 through 9.4. And today is the 14th. But I'll take any questions you have on anything. First, we did start sequences last time. We said basically that a sequence converges to some value if and only if the nth term has a limit as n goes to infinity. As long as the nth term has any limit, as long as it's a finite real number, the sequence converges to that limit. So any questions on any of those? Yes, Sam.
Are those notes on YouTube?
He's putting them up tonight. I gave them to him today. They're going up.
This should be up tonight.
Yes.
Okay. Cool.
And I also have a list of the for the rest of the semester. Okay? This is what's going on the rest of this whole semester. The 11th, that was Monday, we did sequences. Today we're doing 9.2 through 9.4. Partial sums, nth term tests, geometric series, telescoping sums, and comparison tests. Yeah.
So after today, we only have 4 sections left for the semester.
Basically, that's about right. Then on Monday, there are no classes. Okay, no classes on Monday. And then next Thursday, we're going to do 9, 5, and 6, alternating series, ratio test, root test, things like that. And 9, 8, power series, radius of convergence, interval of convergence. And then on the 25th, which is the Thursday, I guess. Must be a Thursday. Yes.
11 days.
No, wait, it can't be a Thursday. It's a Monday. We're going to finish with Taylor series. It's an awesome finish. It's awesome. Anyhow, then the 28th, 2 weeks from today, we do a lab and review. We'll have the test in Chapter 9 the 2nd. Okay? And then 5.5 is a review for the final, and that review is going to take the shape of this. What I'm going to do is pass out a sample final. You're going to work on it. You're going to bring it up to me. I will actually correct it. It'll be a multiple choice 25-question test, very similar to the final. I will correct it up here. I will tell you what your score is on that final. I will have WebAssign tell me your homework grade. I will have your other test scores and your lab score. I'll take all these scores, okay, and tell you what your grade is at that moment. If that's a grade that's acceptable to you, you're done. If it's not acceptable to you, then what? You could fix up homework scores, okay? You could do labs, okay? Some of you haven't done a heck of a lot of labs, and the lab is a test score, okay? You could do labs, or you could come in the following class on the 9th, which is now, we're talking about a Monday, I guess, Monday the 9th. You could take the final exam. It'll be the second form. Similar questions, not the same, but very similar. Same format, 25 multiple choice questions. Okay? That's the whole semester right there. Any questions on that? Okay? Everybody understand? Any questions on anything?
So
yes?
The 28th is a review for Chapter 9 test?
The what is?
On the 28th.
28th is a lab and review for the Chapter 9 test, yes. Yes, it is. Okay. All righty? Okay. And this is Monday's notes? Or you rather see the video?
Yeah.
Okay.
I'd rather just focus on right now.
Okay. All right. So let's get started. We're now going to be talking about a series. Okay. The series that we're going to be looking at will be of this form. It'll be the sum. I equals 1 to infinity of a sub I. Okay. Which means what? This is sigma notation. It means add these things up. Add a sub 1 plus a sub 2 plus a sub 3, etc. Okay? Called an infinite series or a series. Another form of writing this would be like this. I equals 1 to n. Take the limit as n goes to infinity of a sub I. These two mean the same thing. Actually, the second is more proper notation as opposed to using infinity as an index here for the series. The point is, we have a sum now. In a sequence, we had a list. And that list converged as long as the nth term had any limit. But for the sum to converge, the sum must be approaching some number. It must have a limit, okay? So, we have a couple things here. Let's take a look at what are called partial sums. The first partial sum is the first term. The second partial sum is the sum of the first two terms. The third partial sum is the sum of the first three terms, etc. The nth partial sum is the sum of the first n terms. The series converges if the sequence converges, okay? As n goes to infinity, okay? As long as the sequence converges. And we said a sequence converges as long as the nth term has a limit as n goes to infinity. Let's do an example. Let's take a look. Let's see what we got here. Okay? Let's suppose we have this series. Let's do 3 over 10 to the I. Okay? Let's take a look at this. Well, let's see what series that is, first of all. When I is 1, it's 3/10. Plus. When I is 2, we got 3/100. Plus. When I is 3, we got 3/1000. Okay? That's our series, okay? And we're taking the limit as n goes to infinity, okay? Actually, your book uses this notation, now that I think about it. Our WebAssign uses this notation. This is not really proper notation, but this is what it uses. Okay? This notation is the same as this. This is improper, but that's what's used. Why do they use this? I'll tell you why they use this. It sounds silly, but they save a few spaces each time they write it. And over time, they save a few pages. And over all the books, they save a few thousand pages and save money, basically. So what does this mean? Start n at 1 and go to infinity. Keep on going, okay? This is the same thing. It's 3/10, 3/100, etc. Okay? Well, let's take a look at the sequence of partial sums here. What's the first partial sum? In this, it's 0.3. What's the second partial sum? 0.33. And what's the third partial sum?
0.333.
Thank you. Okay. These keep on going. Okay. The nth partial sum would be 0.3333 n times. The question is, why can't we see this? The question is, does that sequence converge? Does it have a limit as n goes to infinity? What's the limit as n goes to infinity of this sequence of partial sums? 1/3 is correct. This is a series that converges. It converges to 1/3. That sum, okay, converges to 1/3. That sum is getting closer and closer to 1/3. This is a concept the Greeks and the Greek mathematicians did not have. The concept that an infinite series, an infinite number of terms, could have a finite value, okay? Here's an infinite number of terms. It has a finite value when we add them up to 1/3. That series converges. Now, it would be nice if our series, a lot of our series, we could just do this with, but we can't, okay? This is kind of an unusual one, all right? We need tests to see if things converge. And not only that, we need a couple of different things to find out what the sum actually is. We can find this sum. This sum is 1/3. That one's not too bad, all right? But there's another test that we need. Another test we need is the Nth Term Divergence test. It says this, basically, given this series. Okay. And this means start n at 1, go 1, 2, 3, etc. Sum these up. Okay, etc. If the limit as n goes to infinity of a sub n, the nth term, is not 0, if the nth term is not going to 0, okay, then the series diverges. Okay? If the nth term does not go to 0, that series will diverge. So let's take a look at some example. Let's suppose we have this. Let's use n. Okay. Let's take a look at this one. That's 1 plus 2 plus 3 plus 4, etc. Does the series converge? Does the sum exist as n goes to infinity? Is the sum some finite real number? That's what it means to exist. Okay?
No.
No. What's that?
Is it a factorial n?
No. This here, that sum, actually the sum of the first n integers is n plus 1 over 2. But if you're taking the limit as n goes to infinity here, this is going to infinity. Okay? So this does not converge, it diverges. Okay? That's the actual sum. As soon as you stop, you can figure out the sum. But if you're going to let n go to infinity here, like we have here, this thing is going to go to infinity. The nth term, n, here, what's the limit of the nth term as n goes to infinity? The nth term is n. That limit does not exist. It goes to infinity. Okay, does not exist. It increases without bound. In other words, the nth term is not going to go to 0. That series diverges, does not have a finite sum. Yes?
Why do you have two tests if you could count them in the first place?
Say that again now.
Like, why are there two different ways of testing it if you could already tell from using the first way?
Okay, so this is one test. What are you saying?
The first thing that you did was like you took all the sums and you saw
Oh, yeah.
divergence, but then the second thing you used.
Oh,
the
because
second test.
there are many times when we can use the first and can't use the second, and vice versa.
Oh, okay.
Yes.
But they're not going to like contradict each other ever?
Never.
Okay.
Never. If the nth term is not going to go to 0, that series will diverge. And if it does diverge, then you know what? That sequence of partial sums will not does not have a limit either. Yeah, they won't contradict each other. And I got to tell you, Abby, we're going to have about 8 more tests for convergence too. We're going to have a ton of them. Okay. So sometimes, if you can use this one, that's nice, because that one's usually pretty simple to apply, but it only applies in a very limited number of cases. Okay? This one here, the Nth Term Divergence test, we'll be able to use quite a bit, but not always. The problem with this one is this, and you got to be careful here. If the nth term does not go to 0, we know the series will diverge, won't have a finite sum. The problem is, what happens when the nth term does go to 0? If it goes to 0, that does not guarantee its convergence, okay? Because it has to go to 0 fast enough to cause the series to converge, okay? I'm going to tell you this. we're going to have a test for this, and I'll do it right now, but we will have a test in a little bit. Let's take a look at this series. Okay, this is called a harmonic series. Okay, has to do with music and all, plucking guitar strings. This series is this. Okay, now, what about the nth term, which is 1 over n? What's the limit of the nth term as n goes to infinity?
0.
0. Does that mean the series converges? Answer, no. It does not mean that. This theorem here, this if-then statement, means if the nth term doesn't go to 0, the series diverges. It does not say if the nth term goes to 0, it converges. Okay? That is not the case. All right? You got to be very careful about that. All right? This is a series that diverges, even though the nth term does go to 0. This is a diverging series. Okay? In other words, the sum of all these gets greater than any real number. It's amazing. If you do this in a computer program, just put the simple series in a computer program. Have a computer just keep on adding the next term. Keep on adding. Caroline, how you doing? And keep on adding the next term. Most computers will end up at about 14 and then will not increase from there. And it looks like it converges to around 14. But what happens? It's the internal representation of the numbers that fails. It's the computer that's rounding these things off when the digits get so long, and it doesn't increase it at all. So it stays at 14. The numbers are so small that the increment is nil, is nothing. So the computer reaches its limit. This series diverges, gets beyond any real number. This series which is 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25. What's the limit of the nth term in this series?
0.
It is 0. But you know what? This series converges. And if you think you've seen something similar to this before, you're right. Because when we were doing improper integrals, and we did 1 over x, and we did that integral from 1 to infinity, we saw the 1 over x went to infinity. It diverged. And then what did I do? The second one I did was 1 over x squared from 1 to infinity. And what did we find out about that integral of 1 over x squared as we went from 1 to infinity? You remember what happened with that one?
It was like, I thought it didn't even get bigger than 1.
Correct. That's exactly correct. The integral was equal to 1. It converged to 1. Okay? The area under that curve is exactly 1. Is there a relationship between these two series and those two integrals? Yes. We'll have an integral test. Yes, go ahead.
But how can it be 1 if 1 is already up there?
No. Okay. You're right. The integral, hold on.
I was thinking area under the curve.
Yeah. This integral, because it converged to 1. That gives us the area under that curve. That does not give us the sum of the series. But what it does tell us is this. Because this integral converged, the series will converge. Does it converge to 1? Obviously not, because of what you just said. Actually, this series is really interesting because the sum of this series is pi squared over 6. That's what the sum actually is, which is amazing. How pi squared gets in there is just amazing stuff, okay? It's just mind-boggling. All right, but anyhow, so we're going to have that integral test a little bit later on tonight, maybe 11:30, something like that. All right, so here's what we have right now. We have 2 tests so far. One test is the sequence of partial sums. If that sequence of partial sums converges as a limit, the series will converge. Second test we have. Divergence test. If the nth term does not go to 0 as n goes to infinity, the series will diverge. Okay? But you have to be very careful and not jump to the conclusion if the nth term does go to 0, the series will converge. That's not true. Okay? In other words, the nth term must be going to 0 in order for that series to have an opportunity, a chance at convergence. And it has to go to 0 fast enough to cause the series to converge. And the rest of tonight and next class will be developing all these tests that will give us some convergence, okay? All right, how are we doing so far? You guys okay? I don't wait. Sammy, you're right on top of this. Okay. Uh-oh. Wait, I brought in more paper, didn't I? Wait, somebody stole my paper. Wait, hold on. No, I have paper.
I mean, it's
No.
from your office.
I know it is. I know you stole a bunch. No, I brought other paper.
I saw those boxes of it in there, so I didn't feel too bad.
Yeah. It's not like I paid for it, that's for sure. Okay. All right, so here's what we're going to do next. There are a couple of series where we can actually find the sum when they converge, okay? So let's do those two first. The first one is called a geometric series. A geometric series is one that can be set up this way. It's the sum. Usually they start at 0 and go to infinity of a r to the n, where a is some constant. R is a constant too. R is called the common ratio. The series looks like this. When n is 0, we get r to the 0, which is when we get a, the constant. Okay? Plus. When n is 1, we get ar. When n is 2, we get ar squared. When it's 3, guess what? We get ar cubed. And it keeps on going. Okay? This is the common ratio. It's what's used to get the next term. Every term is multiplied by this ratio r to get the next term. Okay? For example, let's take this series. How about 2 times 1/2 to the n? This would be a geometric series because it can be written in this form. When n is 0, you get 1/2 to the 0, which is 1, you get 2. Plus. When n is 1, you get 2 times 1/2, 1. When it's 2, we get 2 times 1/4, okay, which is 1/2. The 1 gets multiplied by 1/2. The next term, the 1/2 gets multiplied by another 1/2. Then by another 1/2. This is a geometric series, okay? Geometric series. Now, the question is, when does the geometric series converge and when does it diverge? Okay? Well, let's take a look at that. Let's find the sum of the first n terms of a geometric series, okay? Let's just, instead of going out to infinity, let's take the first n terms. ar squared, ar to the n minus 1. That would be the sum of the first n terms, okay? Everybody okay? What I'm doing is making it finite, and then I'm going to take the limit as n goes to infinity, okay? So the sum of the first n terms would be this. If I multiply both sides by r, I get r times s sub n is equal to ar plus ar squared, ar cubed, ar to the fourth. Okay, I'm multiplying each one of these by r.
Wait, wouldn't that just be ar to the n because n equals 0 in the first case?
All right, so what do you want to do?
Wouldn't you have and on the row above it, you have the last term as AR is n minus 1, but
Yeah.
the first term is n to the 0,
Yes.
so that it's not just AR to the n?
No, because the first term is r to the 0, one less. The nth term would be r to the n minus 1, one less. Well, check it out. Here's the first term. Here's the first two terms. When n is 2, you've got r to the first power. When it's 3, it's to the second power, because you start at 0.
Okay.
And you get n minus 1. You get one less. Okay? Okay? Now I'm going to subtract the 2. Watch this. I'm going to take the top one minus the bottom one. Now, what happens? Here's what happens. I have A. But what happens to my ARs when I subtract first minus second? They cancel. And what happens to the AR squares? They cancel. AR cubes, AR to the fourths, AR to the n minus 1s. This guy is the only one left here. Okay? All the middle terms canceled right out. I'm going to factor out an S sub n, the sum of n terms. Factor out an A. Okay? And now I'm going to divide by 1 minus r. Okay? Here's what I have. The sum of n terms of this geometric series is equal to A, the first term, times 1 minus r to the n over 1 minus r. Now the question is, for what value of r will this be finite? Okay? If r is greater than 1, raising r to the nth and letting n go to infinity will have this go to infinity, and the sum will not exist, because I'll have 1 minus something going to infinity over 1 minus r, whatever that is. R itself is a constant. Does that make sense? If n is less than negative 1, and I raise r to that nth and then let n go to infinity, the same thing happens, okay? If r is like negative 2, when I take negative 2 and raise it to the nth power, and then let n go to infinity, what happens? Then negative 2, well, it goes to negative 2, then 4, and then it goes to negative 8, and then it goes to positive 16, then negative 32, then positive 64, and then negative 128, okay? And there is no limit there. It bounces back and forth, okay, heading to positive and negative infinities. If r is equal to 1, what happens? We have a problem. We have 1 minus r over 1 minus r. We have a division by 0. We have 0 over 0 in determinate form. And if r is negative 1, what happens is we get a minus a plus a minus a, and that limit doesn't exist either. In other words, if r is negative 1, check it out. You get a minus a plus a minus a, and that limit does not exist. Although there's a very famous series that was examined in the 1700s to various conclusions. But the limit does not exist. Okay? The only time this limit exists, this sum actually is finite, is when r has an absolute value less than 1. All the other times this limit will not exist as n goes to infinity. Here's what we have. The sum of that infinite geometric series, when n is going to infinity, is equal to, now, if r has an absolute value less than 1, what happens to r to the n as n goes to infinity? No.
When r is less than 1?
Yeah, when absolute value of r is less than 1, what happens to r to the n as n goes to infinity?
Going to 0.
Goes to 0. I'll tell you, Sam is right on it. Whatever he says happens. Okay? It goes to 0. This goes to 0, and the answer is a over 1 minus r. Okay? So here's the deal. In a geometric series, If r has an absolute value less than 1, that geometric series will converge and have a sum of a over 1 minus r. If r has an absolute value not less than 1, greater than or equal to 1, that geometric series will diverge and not have a finite sum. Okay? Let's do some examples. Well, we already did an example of one.
So how would you rate that answer?
Let's do it. You ready?
Well, like the converge and diverge, because like it can be both for that. So if you were to like,
Depends on r.
okay,
Depends on the rate.
What's the ratio? Okay? Yes.
I have a question on that.
You have a question on this? Go ahead.
Up there when you were subtracting them, how did that last AR and minus 1 cancel out?
It cancels out with a term that comes right before this guy. Okay.
Does that always happen?
Yeah. When I do it, it does. Maybe when you do it, it probably wouldn't happen, but when I do it. No, it will. It will happen. Okay. All right. Let's do some geometric series. I'll tell you what. Let's do the first one. The first geometric series we should do is the Zeno paradox one. Okay? You familiar? I did the Zeno paradox one. I mentioned it, didn't I? The Zeno paradox one basically is, there's a bunch of forms. One form of the Zeno paradox is the hare and the tortoise are going to have a race, and so the hare says, "This is no, I'll give you a head start." So he gives the tortoise a 100-yard head start. Okay? And let's suppose the hare can travel that 10 yards a second, and the tortoise goes 1 yard a second. Okay? So it takes the hare 10 seconds to catch up to where the tortoise was. In those 10 seconds, the tortoise will go an additional 10 yards. Well, now it takes the hare 1 second to get up there. And in that 1 second, okay, the tortoise will go another 1 yard. And then it takes the hare a little bit of time to catch up, and then the tortoise goes a little bit more distance. And it takes a little bit more time for the hare to catch up, and in that time, the tortoise goes a little bit more distance. The conclusion is the hare never catches the tortoise, okay? Because he always has a little bit more distance to go to catch up to him. Okay? That's one form of the Zeno paradox. Another form of the Zeno paradox is this. If you put a student, okay?
The arrow?
The arrow one, yeah, I did this, didn't I?
yeah, you did.
Yeah,
Oh, yeah. I think you didn't say the name, the
I didn't say Zeno paradox? Oh, what I call it, the Burns paradox?
Maybe just, I think you
Maybe you're
only
just
told the
telling
story or something.
Yeah, you're just telling us about it.
Yeah.
Oh, okay, well, now we're going to do it. Okay, now we're going to prove it. Okay, let's put the student up there, shoot the arrow at the student, and what happens is the arrow has to go halfway. Okay. And then the arrow has to go half the remaining distance. And then the arrow has to go half the remaining distance. And then the arrow has to go half the remaining distance. And then the arrow has to go half the remaining distance, half the remaining distance, half the remaining distance, half the remaining. There's always half the remaining distance left to go. The arrow never reaches the student. Okay? We should try.
Burns, have you ever tried, like, I mean, I guess it would be weird, it'd have to be like an info conference in town, but like wait till somebody shows up with an arrow wound and then explain to them they never got hit with it?
Yeah.
No, they're still waiting to get hit.
Yeah. There's some possibilities here. Well, let's take a look at this. What do we have here? What kind of a series do we have here? Well, let's see. The distance is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus,
Could you pull that down?
oh, okay. That's the distance the arrow has to travel. It's an infinite series. What kind of infinite series is it? It's a geometric series. How can you tell it's geometric? Because each term is multiplied by the same common ratio r, which is what? What is each term multiplied by to get to the next term? 1/2. That is correct. So, this is a geometric series. Where we have, I'm going to do it this way, 1/2 times 1/2 to the n. Okay? I'm going to write it that way. A r to the n. Okay? R is 1/2. That's what I have to multiply each term by to get to the next. When n is 0, check it out, you get 1/2 to the 0, which is 1, you get 1/2. Plus, when n is 1, you get 1/2 times 1/2, 1/4. 2, 1/2 times 1/2 squared is 1/8. Now, does this geometric series converge? Yes. Why? How do you know it converges?
Because the absolute value of R is less than 1.
That's perfect. That's exactly right. Thank you, Peg. Because the absolute value of R is less than 1. As long as the absolute value of R is less than 1, the geometric series converges. Not only do we know that it converges, we know what it converges to. We know what the sum is of this. The sum of this geometric series is equal to A, 1/2, over 1 minus R. That's what we just proved. We just did a proof. A over 1 minus R. That's 1/2 over 1/2, which is equal to 1. In other words, the distance traveled by that arrow is the distance, is 1. It reaches the student. Okay? It travels the whole distance. There's an infinite series with a finite sum of 1. Okay? Everybody with me? What about this one? This is an interesting one, I think. I think this one's cool. Let's take a look at this series. 0.9 plus 0.09 plus 0.009 plus 0.0009 plus etc. Is this series geometric?
You just did this one.
What's that?
You just did this one.
Well, threes.
I did this similar one with 3s. Is this one I like this one better though. Is this one geometric? Probably. It's the only one we've done for Pete's sake. Yeah, the answer is yeah. How do you know it's geometric? What's the R? What's the common ratio that's used to get to the next term? 1/10. What's A here? 0.9. Thank you. It's a geometric series where A, the first term, is 0.9, R is 0.1. Does the series converge? Sure. Our absolute value of R is less than 1. What's the sum of this series? Let's see. The sum of this series is equal to A over 1 minus R. That's 0.9 over 0.9. Well, what the heck is 0.9 over 0.9? 1. This is equal to 1. In other words, what we just proved is that 1 is equal to 0.99999 repeating. Is that true, that 1 is equal to 0.9999 repeating? The answer is yes, it's true. It's not only a limit thing, it's exactly equal to it. 1 is equal to 0.99999 repeating. Every real number has two representations, okay? A finite one, decimal, and an infinite repeating decimal. It's kind of interesting, okay? And how do you know they're the same? Because there's no number between these two, okay? If two numbers are different, there must be another number between the two. And there's no number between these two guys.
But isn't the one number right, like infinitesimally, like some increments smaller?
No. If you continue this with a dot, 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 and never end the 9s, they're equal. If you stop, you're right, but you don't stop. Okay? All right, you guys do one. I don't know. I don't know where you guys are. I'm looking around, and I don't know. I see some people are with me, but I see others that are not. Okay, so let's do, you guys do this one. Let's suppose we have this one, 2 plus, I might as well make it interesting with a negative here. Okay, negative 1/2 plus 1/8 plus negative 1/16, etc. Find the sum. Jimmy! Oh, my stapler! Cool.
Thank you.
Do an infinite geometric series. Point. We just.
No wonder it's taken a long time.
Sometimes they get it. I don't know. Well, they're doing a problem now. Sometimes they're okay, but
They
a
don't
lot of the jokes kind of go over their head, you know.
really.
Yeah.
That's 20, I'll put it back in your office.
No problem. Hey, thanks.
I need to replace what I could.
All righty. What's up? Oh. What? You dropped my keys out the window or something? Uh-oh.
Thank you, sir.
Hey, no problem. 0.999 repeating equal to 1. I love that one. That's cool.
Yeah.
That's cool. It's good stuff. Yeah, we did the geometric. We'll do the telescoping. We'll do the integral test today. It's good stuff.
Long time since I taught that.
You'd be good. You were always good. You were good at it. You were good.
It's amazing.
You know, when I retire, man, I don't know. Maybe you'll have to. They'll bring you back to teach them all again. I don't know who's gonna. By count 3, for example, I don't know who's gonna do that. Oh, Gene would do that though.
Three's great.
Yeah, that's the most awesome course. That
I
is.
love the vector calculus.
Oh, it's good stuff. It is good stuff.
It is.
It is.
Does that mean I'll still be working?
Probably. I'm going to do what you do. I mean, not to every college in the state like you do it though. But I'll teach a couple classes here. I think that's my plan. I really don't
You
know.
don't want to go to. You don't want to visit every college in Springfield in the same day, huh?
No. Is that what you
Except
do?
AIC. I don't make AIC.
Is that right? Would you go to Springfield College? You go to Winnick? You do the whole. Jeez, I couldn't do that.
Actually, I think I only have to do 2 a day.
Oh,
But
really?
there's been times where I had to do 3.
Oh, I can't do that. There's no way. No way.
It's tiring. I went home, took a nap today.
Yeah. Well, yeah. I've done that plenty of times. Not to your house, of course, but.
I'm just happy I woke up. At my age.
You're fine.
You laughing at me again?
Egg? Oh, yeah. He's a jokester. I don't know. I forgot the answer. I don't know what the answer is. Yes, what's the answer? Rabbi?
-2.
-2, he says. I don't like -2.
I got -3/4.
-3/4? I don't know. What do you got? -8/5?
I got
Positive
I got
8/5?
positive 8/5.
Oh.
I got positive, not negative.
Let's figure it out. First of all, you got to recognize it's geometric with an A equal 2 and an R -1/4. Okay? Each term is multiplied by -1/4 to get to the next. Since R has an absolute value less than 1, it converges. What does it converge to? In other words, what is that sum? A over 1 minus R. 2 over 1 minus R. That's 2 over, add the opposite, or whatever you do to subtract a negative, okay, wherever you were taught, okay. It becomes 1 plus 1/4, which is 5/4, and that multiplied by the reciprocal gives you 8/5. Okay, so that's 8/5. All right, any questions in geometrics series? Okay. You'll have a couple of those on your test, okay? I'll ask whether it converge or diverge. If it does converge, find the sum, okay? All right, there are other series where we can actually find the sum. Let's take a look at this. Take a look at this series. These are called telescoping sums.
Good Lord.
Wow, telescoping sums. Boy, I can tell you, my writing is getting worse and worse. Let's do it. Let's suppose we have something like this. What I'm going to do, well, I'm going to go to infinity first, but I'm going to do this in a slightly different way. And let's suppose we have 1 over n plus 1 times n plus 2. Okay. Let's write out a few terms. Let's see what we got here. When n is 1, I've got 2 times 3, I have 1/6. When n is 2, I've got 3 times 4, 1/12. When n is 3, I've got 4 times 5, I've got a 20th. Okay. When it's 4, I have a 5 times 6 is 30th. First of all, is this a geometric series? No, it is not. The same r is not used to generate the next term. You can multiply the 1/6 by 1/2 to get 1/12, but 1/12 times a half is 1/24th, not 1/20th. It's not geometric. Okay? It turns out, though, we can actually take this series and find its sum. And here's how we're going to do this. The first thing I'm going to do is find the sum of k terms of this series. And then what I'm eventually going to do is let k go to infinity, okay? But first I'm going to do k. And when we do this, I'm going to get my 1/6, my 1/12, my 1/20th, like before. And then when it's k, I have 1 over k plus 1 and k plus 2. That's the sum of the first k terms of this series. Then what I want to do is let k go to infinity. But before I do that, I'm going to rewrite this series in a different way. I'm going to take the 1 over n plus 1, n plus 2. I'm going to use partial fractions to rewrite this series. Okay? And solve for a and b. Well, you guys know how to solve for a and b. Solve for a by multiplying by n plus 1. Let n equal -1. A is equal to 1. Multiply by n plus 1. This is gone. Let n equal -1 plus 2 is 1. The only thing left standing here would be the a. We solve for b by multiplying by n plus 2. And let n equal -2. -2 plus 1 is -1. So b is -1. So what I can do is rewrite this series this way. And instead of plus and -1, I'm going to write minus. Okay? Well, let's see what happens here. When n is 1, I end up with 1/2 minus 1/3. Which, please note, 1/2 minus 1/3 is 1/6, yes. Plus, now when n is 2, I've got 1/3 minus 1/4, which is equal to 1/12. Plus, when n is 3, I've got 1/4 minus 1/5, which is equal to 1/20. Why is that so funny? I don't know, but it's funny. Okay. Plus, when n is k, I've got 1 over k plus 1 minus, I'm probably off the page, huh? 1 over k plus 2. Can you guys see that? Yes. Whoa, if I just, oh, yeah. Okay. That's what I have for the first k terms. Now keep in mind, what I eventually want to do is let k go to infinity, so I have an infinite series. But in the meantime, what happens here? Well, what happens when I drop the grouping symbols? The 1/3 cancel.
It's equal to 1/2.
The 1/4 cancel. The 1/5 cancel. See this plus 1 over k plus 1? It cancels with the guy right before it, which is a minus 1 over k plus 1. I am left with, out of this whole thing, 1/2 minus 1 over k plus 2. Okay? Hey, good deal. Okay. Wow. Would you write an essay too or something? So, what happened to all the middle terms? They all canceled out. This is why this is called a telescoping sum. It started with this sum of all these terms, and what happened, and when I rewrote it and canceled the middle terms, it collapsed to just these terms, the first and the last. Now, when I take the limit as k goes to infinity, of this sum, yes, exactly. Let's go back to the original, which I rewrote this way here. Shoot, I want the limit here. Okay. I end up with, as k goes to infinity, and that is equal to 1/2 minus what happens to 1 over k plus 2 as k goes to infinity. That goes to 0, equal 1/2. The sum of this infinite series is equal to exactly 1/2. And it's kind of interesting. If you take the partial sums, first partial sum is 1/6. The next partial sum is 1/4 when you add these two. Then the next partial sum is equal to like 6/20, 3/5 or something. Oops, wait, I went too far. Hold on a second, that can't be right. Uh-oh. First partial sum is 1/6. The next partial sum is 1/4. The next partial sum, 1/4 plus 1/20 is 6/20, which is 3/10. Okay, 3/10. What happens is these partial sums are getting closer and closer to what as a limit as n goes to infinity? As the number of terms go to infinity, 1/2. That is the sum of this series. Okay. Now, this is a special series, this telescoping sum. Okay. It has to be in the right form for you to do this. We have to be able to factor it. Okay. This was already given to you in factored form, which is what happens most of the time. It's possible in a web assign they give you n squared plus 3n plus 2, and you have to factor it. Okay, that should not be a big deal. But what we're going to be doing is the product of two linear factors so that we can break it up into partial fractions. Okay? Now there's a little trick here too. You'll notice the difference between the n plus 1 and the n plus 2, if you were to subtract those two, would be 1. The difference in those linear factors tells you how many terms you have left in the beginning and how many terms you have left at the end. Okay? And because the difference in these two guys is 1, I knew I had one term left in the beginning. As soon as I had the 1/2 in the beginning, I could have stopped and said the answer is 1/2. Because what happens is at the end, that always goes to 0. Okay? Those terms in the end. Okay? You with me? You understand what I'm saying? So I'm going to have you guys do one. You ready? Okay, here you go. I want you to find the sum.
Could you pull it down just
What was off, huh? Okay, here you go. Okay. If there's another constant up here, like 2 or 3 or 7 or 10, you can always bring it out front, okay? One of the properties of these summations, these series, any constant can come out front, okay? So I'm going to just have a 1. Let's do this one, n plus 1, n plus 3. Go ahead, you guys do it. Find the sum of that telescoping sum. Bless you. And as you would expect, there's one of these on the next test as well. A couple of geometric ones, but one of these telescoping ones. Done? You got it? I don't know what the answer is. I suppose I could just try to do it in my head. -2 there. Got it? Oh, you got an answer? I don't know what it is. What did you get? 1/8 you got? Anybody disagree with Lewis?
I got 1/4.
I got 1/4.
Lewis. They're all against you. That doesn't mean they're right, though.
Must have helped them.
Not necessarily. Not necessarily. Okay, who wants more time? Nobody wants more time? Well, fine. So we had 1/4 and some 1/8. Would anybody else want to get on record? Saying something else? Okay, let's take a look. You recognize this as a telescoping sum because it's the product of 2 linear factors, okay? First thing to do is use partial fractions to get the constants A and B, so let's do that. Solve for A, multiply by n plus 1, let n equal -1. -1 plus 3 is 2. A is 1/2. Solve for B, multiply by n plus 3, let n equal -3. -3 plus 1 is -2. Therefore, we can write the series this way. I'm going to go to k like I did before. I'm going to take the limit as k goes to infinity. Am I on there? I'm still on there. What do you know? And I'm going to have this as 1/2 n plus 1 minus 1/2 n plus 3. This 1/2 can come all the way out front. You're probably better off doing it that way. Take the 1/2 right out front. K goes to infinity. 1 over n plus 1 of the sum. All right, hopefully that's reasonably. You guys can see that okay? Is that okay? That's okay? Good. Okay, so what do we have? 1/2. The limit as k goes to infinity of this sum. What is this sum? Well, let's see. When n is 1, I'm going to have 1/2 minus 1/4. When it's 2, I'm going to have 1/3 minus 1/5. Well, nothing's canceled so far. Then when it's 3, I'm going to have 1/4 minus 1/6. And then when it's 4, I'm going to have 1/5 minus 1/7. And then when it's k, I'm going to have okay. So we have a 1/2.
Just slide a little bit left.
There. So we have 1/2. What happens here? Well, the 1/4 cancel. The 1/5 cancel. The 1/6 would cancel with the next one. Okay? And what happens at the end? The 1 over k plus 1 would cancel. There'd be this 1 over k plus 3, and the previous term, a 1 over k plus 2, would stay. But as k goes to infinity, those two terms at the end go to 0 anyways. We don't even care about those guys. They're going to 0. You are left with a 1/2 plus a 1/3.
How do you know that the 1/3 wouldn't cancel something?
Because we're already past it. As soon as we get to the 1/4, there's nothing ahead that's going to get us back to 1/3. Okay.
That's what I did too. I just assumed it would all cancel.
Yeah, you can make that assumption. If you know the little trick, since the difference in these two linear factors is 2, there's 2 terms left. There they are.
Why didn't you say that at the start?
I did say, I said it before. I said it a little while ago. Did I say it or what?
No, you did. No, you did. Say
What?
That. You said that on the last one, but I thought it was just on the power of them or something. But it's the difference between the two terms.
The difference between the two.
Of the
Guess what? Now, guess what?
That's no.
We have a recording here. Where this is recorded, we have evidence that that's what I said. Now, we could put a little wager on this if you want to see it. No, let's not get there. All right? No, all right. Here's what I'm telling you. The difference in these two linear terms here is 2. N plus 3 minus the n plus 1 is 2. That tells you there's going to be 2 terms left in the beginning. Okay? If this were an n plus 1 and an n plus 4, there would be 3 terms in the beginning. Okay? Because that difference is 3. This is all that remains. The answer then is 1/2. This is equal to 5/6. Okay, right? 1/2 plus 1/3 is 5/6. Hey, what did you guys say? Is it 5/12? Is that what you said?
That's what I said.
That's what Lewis said, and you guys didn't. I should have bet on you, Lewis.
That's happened.
Although I don't even think you said 5. Wait, why did you guys get it wrong?
Because we all just saw the 1/2 in the
Yeah.
front and called it done. Like our
Oh, man. Oh,
everything they cancel in the
man.
middle. Like,
Oh,
You said that the first term would be the. You said, oh, once we get the first term, we can stop here.
Because, yeah, well, wait a second. I said, because the difference in these is 1, I knew there was only 1 term left. The difference in these two was 1. There's only 1 term. The difference in these two is 2, so that I know there's 2 terms.
see, that's noteworthy right there.
Yeah, I know it, and that is on the video. You will see if you take a look at this after Devin puts it up
You know
there.
what? We're stopping class. We're watching that video right now. We're gonna get some answers.
We should do it. We should do it. No, it's on you.
I'll collect the wages.
Oh, Yeah, put them in there. Okay, everybody else set on this? That's the kind of thing you're going to see on the test. You're going to see one of those, I'll ask for the sum. All right, what else do we got? Well, those two series, geometric series, telescoping series, are really the only two series where we actually find the sum when they converge. What we're going to do now, the rest of class today, and the whole class on Thursday. Geez, I don't even see you guys for a week. Wow. Is determining whether the series does converge or not. If it does converge, that'll be sufficient. We'll say it converges. We won't find the sum. Okay? We merely want to know if it converges or not. Okay? So we're going to have some tests for convergence. First test for convergence, outside of the geometric and telescoping one, is called an integral test. Given series okay, where the a sub i's, these a sub n's, are positive, okay, they all have to be positive, and decreasing. Okay? They have to be positive and decreasing, okay? Positive series and decreasing. You can't have any zeros, can't have any negative numbers in there. It's got to be a decreasing series. Then, oh, I'm off. Shoot. Then, the integral from 1 to infinity of this nth term, okay, and I'm going to use an x here because we're going to use x's here. In other words, the series sums up is discrete. It sums up 1/2 plus 1/3 plus 1/4, say, plus 1/5, etc. Okay? And what we're doing is connecting those with a continuous function. That's our function we're going to integrate. We're going to connect the dots with a function. Okay? I'm going to call it a sub x. Okay? So this will be, say, 1 over n, but this will be 1 over x. It connects those dots. Because we can only integrate continuous functions. We can't integrate a sequence of dots. Okay, discontinuous function. dx. Okay. This integral and the series converge or diverge together. They converge or diverge together. Now, because the integral converges to some number, that does not mean that that number is the sum of the series. But if the integral converges to some number, some finite real number, the series will converge. Not necessarily to that number, but it will converge. It will have a finite sum. Okay? For example, everybody all set with this? Dylan, you okay with this? For example, if we have the series okay, this is the harmonic series. Okay, it's the harmonic series. We can test for its convergence by using an integral test, by doing the following. We'll integrate from 1 to infinity, 1 over x dx. Notice I'm replacing the n with an x here. Okay? And we can do this by finding the limit as b goes to infinity, 1 to b, 1 over x dx. If the integral converges, the series converges. If the integral diverges, the series diverges. Okay? Well, hopefully you remember this series already, but if not, let's do it out. So limit as b goes to infinity, natural log x, still limit, b goes to infinity, natural log b minus the natural log of 1. Okay. Now, as b goes to infinity, what happens to the natural log of b? Yeah, it goes to infinity very slowly, but increases without bound. Natural log of 1 is 0. The problem is, the fact of the matter is, this goes to infinity, and that integral diverges. Because the integral diverges, the series diverges as well. Okay? So that harmonic series diverges. Okay? It diverges. Let's try another one. This is
You
one.
can interpret that because you still have b, it's like a multiplying factor in there.
Say that again now?
B is still, when you do the integral, it's still a multiplying factor in there, so you know you're going to get an infinity. It's not like dividing by infinity.
Yeah, yeah, and the next one we're going to divide by infinity, so you'll see it. That's correct. Okay. Let's do this one. Okay, I already mentioned this one, but let's prove it now. Okay. Let's take a look. This series will converge or diverge depending on the integral of 1 over x squared. We'll take the limit. B goes to infinity. 1 to b, x to the negative second. Okay, that's the limit. B goes to infinity. Add 1 and divide. That's equal to the limit. B goes to infinity. I'm going to rewrite it, negative 1 over x. Okay. Substitute in. You get negative 1 over b, minus minus plus 1. Now, as b goes to infinity, what happens to negative 1 over b?
0.
Goes to 0. This is equal to 1. The integral converges to 1. The area under that curve was exactly 1 square unit. It has an infinite perimeter with a square area. I mean, with a finite area of exactly 1 square unit, which is amazing in itself. Because the integral converges, the series converges. It has a finite sum. It does not mean that the sum here is equal to 1. And we saw it can't, because it already starts off at 1 and then goes up from there. Okay? But what it does tell us, it tells us that the series does converge. And like I said, this series has a sum of pi squared over 6, which is amazing. Okay? It's incredible if that would be the case. Now, I did 1 over n, I did 1 over n squared. What happens with this one? Can you tell me what happens to this one without doing the integral out? This would be an integral test kind of a thing. What is this series? Does it converge or diverge?
It's going to converge at 3 halves.
What is it?
Or it can converge at 1 half.
No. It's going to diverge. Do you remember P series we had from P integrals from the last chapter? Here's the deal. See, this integral is this. Or you can rewrite it this way. It's this exponent that's critical here. This is 1/2. This is a P integral that we said last time, our improper integrals. What did we say about these P integrals? We said they converged if P is greater than 1. And we said they diverge if P is less than or equal to 1. Because those, here, okay, this diverges. Okay? This diverges. Consequently, the series diverges as well. Recall this from last chapter. these integrals. What happens? Converge when p is greater than 1. Diverge, p is less than or equal to 1. That's what we saw last chapter. Okay? Do you remember that at all?
Mhm.
Does that ring a bell? No? Carlos, it doesn't ring a bell at all? Well, you're going to have to trust me now. You trust me? I don't know, you're such a jokester. I never know when you're kidding me or when you're not, though. But, all right, anyhow.
Yeah, right here.
You got it written down?
Yeah.
Sam's got evidence right there. Carl, got evidence. Okay, because this is the case, that tells us about the summations here, the infinite series. Because that's true, what do we know? Well, we have p series. Okay, p series. These are p series. Okay. What do you know about p series? Well, same thing we know about integrals. Okay. They converge if p is greater than 1. They diverge if p is less than or equal to 1. Okay? Yeah, we proved the two, we did it, and it converged. Okay? When p is equal to 1, we saw that it diverged. When p is equal to 1/2, it diverges. Okay? Is everybody with me on this? Ugh. KB, you with me? You are? Okay, good. Okay. KD, are you with me? Okay, good deal. CL, are you with me? All right, good deal. All right. PZ, you with me? PX, are you with me? I'm sorry, I messed it up. I was trying to find P. Okay. Sorry. Okay, so if you have this series, I'm not convinced. Well, I don't know what you guys. All right, here. This series. Converge or diverge? Converge. It's that simple. Okay? It's that simple. What about this series? Oh, well, why don't I write it this way? N.
Diverge.
Diverge. Is it a p series? Could you write this as a p series?
Well, p is equal to 1.
Is p? No, p wouldn't be 1 here. P would be what here? What? No, not 0. -1. P would actually be -1. To write it in the right form, it would be -1.
Oh, sure, yeah.
What's that?
No, because it has to be in the denominator.
Yeah, it'd have to be in the. See, these are p series of this form. P is some integer. So n is 1 over n to the -1st. Negative exponent, take the reciprocal. This is a p series where p is -1.
But in that form, you would drop the -1, though, right?
Say that again now?
Well, since you moved it down, it
Yeah.
would be 1.
All right. I'm telling you that this and this are the same. Do you agree with me?
No, because it's
No, you don't.
denominator.
What's that?
Oh, wait, yeah, because then the negative would cancel.
Yeah, negative means take the reciprocal to a positive exponent, and you get this. These two are the same. I mean, this is, you don't generally write this form. All right, check this out. Make sure a little algebra thing here. Okay, everybody okay? Everybody's all right? Okay. All right. Okay, these are going to be very important. Okay. What do you think, Carlos? You know, you're saying a lot right there. You said a lot. Yeah, doing that. That said a lot. All right. These are going to be very important when we do the next set of tests, okay? We got bunches of tests to go. A long ways to go. Okay? Here we go. These are comparison tests. Well, I should do an integral test that's not a p-series, though. You can use the integral test for other series other than just the p-series. For example, what about this series? Let's take a look at this. Let us look at e to the negative n. Let's take a look at this series. Let's write out a few terms. At 1, we get e to the negative first. 2, we get e squared. 3, oh, wow, we get e. Oh, gosh. Okay, I was going to use an integral test on this, but what else could we do for this series to prove it converges or diverges? What is it?
P-series?
It's not a p-series. It doesn't have the right form. To be a p-series, it has to have this form. And the n has to be going from 1 to infinity. This is we don't have that form. Okay? The e is a constant. It's the n here that's the variable, as opposed to this where the exponent is a constant. What kind of series is this? Yeah, it is geometric as well. I wasn't thinking geometric because I wanted to do it with the integral test, but it is geometric. What's a in this series? 1 over e. The first term. A is 1 over e. And what's r? What do you multiply each term by to get the next term?
E to the n?
No. What is it? 1 over e again. Yeah. A is 1 over e. R is 1 over e. It's geometric. 1 over e has an absolute value less than 1. Therefore, it converges. We could actually find the sum of this series. We'll do it. But I'm also going to do an integral test. The sum of this series is a, 1 minus r, okay, multiplied by e over e. You end up with 1 over e minus 1. That would be the actual sum of this series, okay? 1 over e minus 1, because it is geometric. But if you didn't recognize it as geometric, you could prove it with an integral test that it converges. You would do this integral, 1 to infinity, e to the negative x dx.
Can you just shift the page?
Okay. Okay. We okay? Boy, people are dying left and right on me here. All right, but that's all right. I don't have that much more to go. Take the limit. What's the integral of e to the negative x? What form is that, first of all? Thank you. And u is negative x, or the opposite of x. The du is negative 1 dx. I have to multiply by negative 1 and a negative 1. You take that all the way out front as far as that goes. You end up with e to the u du. The integral of e to the u is e to the u. Okay. Substitute in. E to the negative b minus e to the negative first. As b goes to infinity, what happens to e to the opposite of b? Where does it go?
Goes to 0.
Goes to 0. Goes to 0 because it's 1 over e to the b, and b is going to infinity, so that's going to go to 0. You got a minus, minus, you get plus. You get 1 over e.
So then negative 1. Oh, negative.
Yeah. So what happens here is the integral test says it converges, which it does. It says the integral converges to 1 over e. That tells us that the sum converges. It doesn't tell us that the sum converges to 1 over e. We actually know the sum converges to 1 over e minus 1 because it is geometric as well. All right, is everybody with me on this? What I've done, I proved this series converged 2 different ways. One geometric, which actually gives us the sum, and the second way with an integral test. I'm just saying you can use the integral test on things that are not p-series. Okay? Actually, at this point, you shouldn't have to even test a p-series. You should look at it and say it's a p-series where p is equal to whatever it is, and say it converges or diverges because of it. Okay? All right, how are we doing? You guys still alive? Minus, you still alive? Barely? What's that?
Almost.
Almost alive? That means dead, I think. All right, but anyhow. All right. Almost alive. Let me see. Okay, we have a couple more tests to do. Comparison tests. We have two kinds of comparison tests. The first comparison test is a direct comparison test. A direct comparison test. Let's suppose that you're given 0 is less than a sub i's, which are less than or equal to b sub i's. Okay. The a sub i's are less than or equal to the b sub i's. Then, if the big series, the b's, if this series converges, then what about the smaller series? Yes. If the bigger series is going to converge and have a finite sum, where its terms are greater than or equal to the terms of the smaller series, then the smaller series must converge as well. It can't be going out to infinity if the bigger series has a finite sum. Okay? It's bounded above by that bigger series. And it converges, the smaller series will also converge. If the smaller series diverges, then the big series, yes, diverges as well. Okay? Let's take a look. How about this? Will that series converge or diverge?
Converge?
You bet, Brennan. Did you pitch today or what?
We have a game I didn't pitch up.
What? You want me to contact your coach or what?
I don't know. I'm on seniors on the team.
Are you a senior?
I'm a junior.
Oh. You gonna let me know when will you know ahead of time?
Probably not.
What the heck is that? Oh man. All right. What's that?
Sorry, I'll get you my coach's number and you can tell him.
All right, you give it to me. I'll give him a call. All right. You probably get bounced off the team. All right. It does converge. Why? Because these terms are less than or equal to these terms. When you add 1 to that denominator, it makes the denominator bigger. It makes the terms smaller. These terms are less than these terms. But what do you know about this series here? What does this series do? Does it converge or diverge? What? It converges. It's a p series where p is 2. Therefore, it converges. Okay? Because this converges, it's the bigger series. Its smaller series will also converge. You could do this with an integral test too, by the way. The integral of x squared plus 1 is an inverse tangent, which will converge. Okay? You could do this with an integral test. There's a direct comparison test. Okay? Just compare it directly with some other series. All right? That's known. All right, last one. Here we go. This is called a limit comparison test.
You know it's getting bad when you start numbering things. You end with numbering stuff all semester.
Yeah, this is going to be a problem. here's the thing, though. I'm going to give you 2 wicked good shortcuts for this, where you could do 95% of the series with one of my shortcuts. But I'm not going to give it to you just yet, okay? I could give you one of the shortcuts right now, though, with this one. I probably will. Okay, here we go. Here's the limit comparison test. Okay? Given. Two series. And again, we're going to have non-zero positive terms, okay? We can't have zero terms. We don't have negative terms, okay? Next week, next Thursday, we'll do alternating series, okay? Then, let the limit as n goes to infinity of, it doesn't matter which order you take, b sub n over a sub n equals L. Okay. So you've got these two series. And generally what it is one's known and the other's unknown. Okay? And you form a ratio of those two, their nth terms. And you let n go to infinity and find the limit. If that limit L is finite and greater than 0, okay? In other words, if the limit exists and it's positive, then the series converge or diverge together. In other words, they're increasing about the same rate, okay? Their nth terms have a limit, okay, a ratio. If one's going to go to infinity, the other is 2, and one is finite, the known one is finite, then the other is 2. For example, let's do some here. Oh boy. Here we go. Let's take this one. Oh, let's take 1 over n cubed minus n squared plus 1. Well, there's a series. It's not quite a p-series because of that n squared in there. It messes it up. That's being subtracted. And the 1 does too, as far as that goes. 1 over n cubed is a p-series that converges. The question is, what about the n squared and the 1? How much does it mess it up? Or does that series still converge? And we don't care about the n squared and the n's. It turns out we don't care about the n squared and the 1's, because when n is big enough, it's the n cubed that dominates the whole thing. N cubed would be much bigger than the n squares. Okay? But how do you prove it? You prove it with a limit comparison test. You take the limit as n goes to infinity of the nth term and compare it to this nth term of a known converging series in this case, a p-series where n is 3. And you find the limit. Well, take the reciprocals here. You get n cubed over n cubed minus n squared plus 1. What's that limit equal to of n cubed over n cubed minus n squared plus 1? 1. You could do it because you could use L'Hopital's, that would do it. You got same degree, ratio of leading coefficients is 1. You could divide numerator and denominator by n cubed. There's various ways of proving that. That limit's equal to 1. Which one, Dylan? Now, because that limit's equal to 1, it's finite, it's greater than 0, the two series converge or diverge together. 1 over n cubed is a p-series where p is 3. It converges, therefore our series converges. Okay? Now, let's take a look at another one. Suppose you have this. Let's suppose we had, and let's make it a little bit more complicated here. Let's suppose we had n over n to the 3 halves plus n plus 10. Wow. Wow. Okay. What about this series? Here's the deal. And this is an extremely important shortcut that will cut your work in half for this. Okay? Here's what's critical here. What's critical here is the difference in degrees. Okay? The difference in degrees, numerator and denominator, is 1/2. Okay? That's the difference in degrees. That difference in degrees is 1/2. That tells you that this series will diverge. And how do you prove that it diverges? With a limit comparison test with 1 over the square root of n. That same degree, 1/2. Okay? The difference in degrees is critical. Do a limit comparison test. Okay? With that known p series, 1 over n to the 1/2. Make sure you use the same, whatever the difference in degrees here is, that's what you use with your exponent here. Now, what about this limit? This looks nasty, but it's not. Okay, multiply by the reciprocal, this comes up top. You get n to the 3/2. You get n to the 3/2 plus n plus 10. Those are the same. What's the limit here? 1 is correct. That tells you the two series converge together or diverge together. Converge or diverge together. We compared it with 1 over n to the 1/2. That's a p series where p is 1/2. This diverges, therefore the original series diverges. Yes?
But for difference in degree, was it it's the highest degree in the denominator to the numerator?
Yes, yeah. What you do is take the highest degree in the denominator minus the highest degree in the numerator. Okay, it's denominator minus numerator. 1/2. Because the difference in degrees is only 1/2, you know it diverges. Now, if you had to prove it, you prove it with a limit comparison test like this. That proves that it diverges because you just compared it to the known diverging series 1 over n to the 1/2. Okay? So, if you have this series, okay, just make it this way. What about this series? Does it converge or diverge? What's that?
Don't you have just an n to the second plus 10 on the bottom? Right? Oh, no. It's not.
I'm not sure what you.
No, I mixed up my multiplication.
Okay.
Addition.
Okay. Carolina, what is it? I didn't quite hear you, Carolina. You're going to have to say it a little bit louder. I didn't hear you. Yes, Carolina, yes. It converges. Why? What's the difference in degrees here? 2. That difference in degrees is 2.
Wouldn't you subtract the 4 and 2 though?
Yes, 4 minus 2 is 2. Denominator minus the numerator is 2. Yes, go ahead.
Okay, I get it.
Okay. It's denominator, 3/2 minus 1. Denominator minus numerator. Okay. Denominator minus numerator, 4 minus 2 is 2. The difference in degrees is 2. That's good enough to cause the series to converge. If you had to prove it, you prove it with a limit comparison test with 1 over n squared. That limit would exist as you take the ratio of those two nth terms. They converge together. 1 over n squared is a converging p series. You guys with me on this? Okay. You sure? I'm going to give you one more. And then you're going to write down converge or diverge. And I'm going to go check it. And I need virtually everybody in this class to get it right. And we're going to be done. Karen.
Is there something different that you do with the difference in degrees? off. Did I miss something about?
Did you nod off there for a while? Maybe you did miss something. I don't know.
I'm just wondering, because you said the difference in the degrees is 2, then you can
Yes.
solve it by using the way that you did before, right?
Yeah. Difference in degrees is 2.
Yeah.
That means it's going to converge because when you compare it to the p series 1 over n squared, which converges because p is 2.
Oh, okay.
This one here, it's 1/2 difference. So we know it diverges
Oh, I
because
see.
it's only 1/2, less than 1. The key is whether it's greater than 1 or less than or equal to 1. Okay? Everybody else set on that?
Yeah.
So what I'm telling you is this. You get this stuff on homework. You can look at these things as long as we can talk about degrees. Okay, when you got these kinds of things, the problems are trivial. The problem is when you get factorials involved and exponents that don't have degrees. But that's next. That's coming up next. But I'm going to give you a really, really good way of doing it. Okay, really good way. I'm going to give you one right now. And I need virtually everybody to get it right. I'm going to allow for one error, okay? One mistake. But everybody else has to get it right. Okay, you ready? You're going to write down converge or diverge and not say anything. Okay, here we go. Let's do this series.
Yeah, parents, I'm just putting this out there based on what we're doing. What if?
What if go ahead?
Suppose that some people got it right, and then you had 1/2 of the class go home, and then you gave another problem, and then another 1/2 of the class would go home. Wouldn't it turn out that you were always here?
That's good. I like that. That's very good, Dylan. You should go. You can leave right now if you want. No. That was great. That was great. That's exactly right. That's pretty cool. That was good. Good stuff. All right, here we go. Now, how difficult should I make this? I'm going to make this. Here we go. Here we go. Oh, no. I need you to write converge or diverge on your paper and raise your hand. That's a 4/3 down there plus 10, and that's an n to the 1/3 up there. I need you to write that down. And we need to get virtually everybody get it right. I'll allow for one error. We have room for one. And the error looks like it could be Levi. No, Levi's going to come through. No, he's not going to come through. He's going to come through. You're going to write down the answer. You got to write down the answer to this. You got it? You know what? I believe it. No, I don't. I don't know if I believe it or not. All right, you're going to write down the answer. Everybody's going to write down the answer on a piece of paper. He doesn't have a piece of paper. All right. You write it on your hand. Oh, no. On your hand. No, on your piece of paper. Okay. Okay, when you have an answer, raise your hand. Okay. You're going to write down one word. If both of these guys are wrong, we got another problem to do. Okay? Right. 2 for 2. Three for 3. I hate to be the person. Well, we can have one mistake. We have one mistake. Shoot. We have 2 mistakes. Oh, man, forget it. We're going to do another one.
Wait, what was it?
What do you think it is? Diverge is the correct answer. Why is it diverging? Because the difference in degrees is 1. When the difference in degrees is 1, the series will diverge. That's a diverging series. That's the harmonic series. It diverges. To converge, the difference in degrees must be greater than 1. Greater than 1. Okay, to converge. All right, one more. Same thing. We need virtually everybody. This may be a little tricky for people. This may be tricky. If you got the answer, raise your hand. Write it down, converge or diverge. Correct, 1 for 1. We have one mistake. We can have one more and that's it. Correct. 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 All right, okay. What's that?
I don't trust myself.
Oh, geez, there it goes. Destroyed your confidence. That's not good. We may have to stay until you get your confidence back. So. Who else? Caroline. We have 2 mistakes. We're going to have to do it all. No.
Diverge?
Yeah.
No.
Was diverge.
It's diverge. Why?
Because it's
Negative.
The difference in degrees is -2. What the heck?
I thought you said you can't have negatives.
What? If it's negative, that means it definitely diverges. Not only does it diverge, the nth term of this series here is not going to 0, it's going to infinity. You're adding up things that are increasing to infinity, for Pete's sake. All right?
Look at the P series rule.
The P series, yeah. The P series is the key. The P series is 1 over n to the P. Okay, when you take the denominator minus the numerator, you get -2. If that's if that difference is less than or equal to 1, it diverges. Less than or equal to 1, it diverges. So if it's negative, it definitely diverges. The nth term is not going to go to 0. It's increasing, for Pete's sake. I got to do another one. Oh, gee.
blood pressure.
No, actually not. All right, come on. We can do it. We can do it. Okay, let's do... Do I dare give you this? No, I'll write it this way. This will be better. I was going to put 7 halves, but I'll only do this. Okay. Converge or diverge? Carlos has it immediately.
I got it.
Well,
3.5.
that's a 3.5, yes.
Sounds
Do. Correcto, 1. We're going to get it. Correcto, 2.
we can go.
You didn't raise your hand. Correcto, 3. Think about it. 4. Whoa, really low. 5. What does that say? Oh, the C is outside of it. Okay, 6, 7, 8. Okay, that away, guy. Yes, yes, yes. Where's your answer? What? I need converge or, oh, a C. Yes, yes. 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 Chris knows. Yes. And did I get everybody, I think?
Yep.
Just about everybody? Yes, we do. Thank goodness.
About time.
Holy moly. Difference in degrees, 1.5. Good enough. It's greater than 1. So for homework, you should be doing 9.1 sequences, 9.2, 9.3, and 9.4.
It's like 2-3 weeks. Just get them all.
Do them all tonight.
Yeah.
2 by 12.
See you in a week. What's that?
Still left.
What lab? The last lab? No, the previous lab?
Yeah. I don't know, I don't know what it was due, because I think I wasn't here, so then I didn't.
Yeah. I think the lab was due last Friday. When was your test? When did you take this test?
Monday.
We had the test on
No,
Monday.
Oh, you
it's
did?
due
Oh,
this
so the lab is due
Friday.
Friday this week. So it's not even due yet.
Speaking of the test, am I able to make that up?
Yeah, of course.
Alright, cool.
Wait, so
Let
it's
me
due
know when.
tomorrow?
Alright.
What's that?
So it's due tomorrow?
What's tomorrow?
Friday.
Then it's due tomorrow. Oh, listen, Abby, here's what happened. I will actually look at it Sunday night.
So can I give it to you on Saturday?
Yeah, of course.
Thanks.
All All right. You're such a nice guy.
Uh,
I'm a nice guy.
I'll email you later about
Yeah,
that.
yeah, we can make arrangements.
Professor, I still haven't got the message from Carlos.
You, Carlos Pedro, you sent him an email.
Yeah, I sent him an email, but he hasn't responded yet. It's still on Friday.
Well, we're gonna extend this for you. We'll get this straightened out.
Okay.
Oh, you want me to correct it or something?
Something like that. I also want to get the notes, so it's here for some of it.
Yeah, okay. Comparison test, maybe this.
Professor, quick question.
Go ahead.
That's the recording?
No questions.
No question.
That's the recording?
Oh my gosh, I'm still recording.